In episode 76, titled Web Attack Mini-Scenarios, we're using rapid drills to build web reasoning without heavy technical detail, because good web testing is more about judgment than about payload memorization. In real environments, you rarely get a clean label that says, "This is injection" or "This is access control," and you rarely have the time or safety margin to try everything. Instead, you get a small clue, a constraint, and a decision to make about what the safest, most informative next step should be. These drills are designed to sharpen that instinct, especially for exam-style scenarios where you must infer the right category and action from limited information. The emphasis here is on recognizing patterns, choosing minimal confirmation steps, and avoiding unnecessary disruption. If you can consistently choose the right next step with confidence, you are thinking like a professional web assessor. The drill method follows a simple loop. Identify the clue, choose a test, justify it, then summarize what you learned. Identifying the clue means naming the single behavior that matters most, such as an odd response change, unexpected access, or trust persisting longer than it should. Choosing a test means selecting the smallest, safest action that can confirm or refute your hypothesis, rather than jumping straight to aggressive payloads. Justifying the test means explaining why it matches the clue, respects scope and stability, and produces evidence that actually changes your understanding. Summarizing means you state what the result implies about the control failure and what direction remediation should take. This loop keeps your work grounded and prevents tool-driven testing that creates noise without insight. Over time, the drill becomes automatic and keeps your web testing focused.
Scenario 1 starts with unusual query behavior, which is a common injection clue, but not a diagnosis by itself.
Imagine a search feature that returns sensible results for normal input, but when you include certain characters or patterns, the results change dramatically. Errors appear or filtering behaves inconsistently.
The key clue is that the behavior change feels structural, as if the application is interpreting your input rather than just matching it.
From that clue, you infer an injection family hypothesis, such as SQL injection, because search features often translate input into database queries. The safe validation step is not to drop destructive payloads, but to confirm whether the behavior is consistent and interpreter-driven, using minimal changes that demonstrate control over query interpretation rather than data extraction.
This approach lets you confirm risk without causing service disruption or pulling sensitive data.
The drill teaches you that the goal is to prove input became instruction, not to prove how much data you could steal.
Other choices fail in Scenario 1 because they are mismatched to the phase or the clue.
Jumping straight to command-style payloads is wrong because the feature's behavior points towards a data query, not system execution.
Running heavy payloads that attempt data modification or long-running queries is too risky on a production system and unnecessary to prove the boundary failure. Ignoring the behavior because it might be just a bug also fails, because consistent structural changes tied to input deserved controlled validation.
The correct choice is the one that aligns with the suspected interpreter and uses the smallest test that distinguishes data handling from instruction handling.
When you can explain why the other options are wrong, you are demonstrating reasoning rather than guessing.
That is exactly what the exam is looking for in these scenarios.
Scenario 2 involves an object identifier change that reveals data, which is one of the clearest access control failure patterns. Imagine a user can view their own record by requesting an endpoint with an object identifier, and when you change that identifier to another valid value, the server returns another user's data.
The clue is that the server accepted the identifier without verifying ownership or scope, which immediately points to an IDOR issue.
The safest next step is to confirm the behavior with a minimal number of requests and to test with 2 roles or 2 users, stopping as soon as unauthorized access is demonstrated.
You avoid bulk enumeration or scraping, because one confirmed unauthorized access is enough to establish the control failure. This scenario emphasizes that IDOR requires no sophisticated payloads, only careful observation of how the server handles object references.
The drill reinforces that access control failures often produce the highest impact with the lowest effort.
Evidence to capture in Scenario 2 should be precise and limited, focusing on roles tested, objects accessed, and observed differences. You document the requesting user's role or identity, the object identifier used, and the fact that the returned object belongs to a different user or scope. You captured just enough of the response to show the mismatch without collecting full records or sensitive fields unnecessarily. You also note whether the same endpoint behaves correctly for some objects and incorrectly for others, because inconsistency often explains how the bug slipped through. This evidence pattern supports remediation directly, because developers can reproduce the issue by checking ownership enforcement. The drill teaches that good evidence is about clarity, not volume. When you can show this user accessed this other user's object, the finding is hard to dispute.
Scenario 3 focuses on session persistence after logout, which is a classic signal of weak session handling rather than a password or MFA failure. Imagine a user logs out of an application, but requests using the same session artifact continue to succeed, or access remains possible without reauthentication. The clue is that trust persists beyond the point where the user believes it should end, indicating that logout does not invalidate server-side session state or tokens. From that clue, you infer a session lifecycle weakness, not an authentication bypass. The safest validation step is to confirm the behavior with minimal, read-only requests that demonstrate continued access, rather than attempting state-changing actions. You also observe token expiration behavior and whether credential changes affect the session, because those details define the replay window. This scenario reinforces that many compromises happen after login, not during it, and that session management deserves equal scrutiny.
Safer checks in Scenario 3 are those that prove persistence without causing harm or confusion. You use a minimal endpoint that requires authentication and observe whether it still returns authorized data after logout. You avoid actions that modify data, trigger notifications, or affect other users, because the objective is to prove that the session remains valid, not to demonstrate abuse. You note whether the behavior persists across browser refresh, new requests, or time delays, because that helps classify whether the issue is client-side or server-side.
The drill emphasizes restraint because session testing can easily cross into risky territory if you treat persistence as permission to do more.
When you stop at proof of continued access, you have enough evidence to justify remediation.
That is professional web validation. Scenario 4 involves a URL fetch feature reaching an internal address, which is a strong SSRF clue. Imagine an application feature that retrieves a URL to generate a preview or import content, and you observe that the server responds differently when given addresses that appear internal or restricted. The clue is that the server is acting as a network client on behalf of the user, and the destination is influenced by user input. From that clue, you infer SSRF risk, because the server's network position is being leveraged to reach places the user cannot. The safest next step is to confirm that the server is indeed making the request, and that destination restrictions are insufficient, using minimal, non-scanning tests. You focus on reachability confirmation, rather than on extracting sensitive internal data, because the boundary failure is the core issue. This scenario teaches you to separate server-initiated requests from browser-initiated ones, which avoids confusion with CSRF. Pitfalls across these scenarios often come from assuming impact without proof and skipping authorization checks because something looks technical. Assuming impact means claiming data theft, code execution, or account takeover without demonstrating the necessary control boundary failure, which weakens reports and exam answers alike. Skipping authorization checks happens when testers focus on injection-style testing and overlook simple role or object differences that would reveal higher-impact issues faster.
Another pitfall is escalating too quickly, such as running heavy payloads or broad scans, which can destabilize systems and obscure the original signal. The disciplined approach is to match test to clue, keep scope tight, and stop when the hypothesis is confirmed. These drills are designed to build that habit so you do not default to overtesting. When you avoid these pitfalls, your conclusions are clearer and your validation safer.
Quick wins in web mini-scenarios almost always involve testing with 2 roles and 1 controlled input change. 2 roles help you reveal authorization gaps without complex payloads, and 1 controlled change helps you isolate cause and effect. This might mean changing an object identifier once, toggling a role, or adjusting a single parameter to observe behavior differences. These actions are low noise, low risk, and high signal, which is exactly what you want in time-boxed assessments and exam reasoning. Quick wins also help you prioritize remediation because they point directly to missing checks rather than to theoretical weaknesses. The drill reinforces that you do not need dozens of requests to prove a web issue. Often, one well-chosen request is enough. Reporting language in these scenarios should state behavior, impact, and clear remediation direction without unnecessary technical flourish. You describe what input or action was tested, what the server did in response, and why that behavior violates an expected control. You describe impact in practical terms, such as unauthorized data access, unintended state persistence, or internal network reach, without speculating beyond the evidence. You recommend remediation that matches the failure, such as server-side authorization checks, session invalidation on logout, strict destination allow lists, or parameterized queries. You also note constraints, such as production sensitivity, to explain why validation stopped where it did. Clear reporting makes the finding actionable and credible, which is the goal in both exams and real work.
To keep the drill pattern tight, use this memory phrase: clue, control, confirm, document, recommend. Clue reminds you to start with the observed behavior that matters most. Control reminds you to identify which security control is likely failing, such as input handling, authorization, session management, or request routing. Confirm reminds you to choose the smallest safe test that proves or disproves your hypothesis. Document reminds you to capture minimal, clear evidence that shows the boundary failure. Recommend reminds you to point remediation toward the broken control, not toward unrelated hardening. This phrase keeps your reasoning structured under pressure and prevents you from drifting into tool-driven testing.
To conclude episode 76, titled Web Attack Mini-Scenarios, remember that the drill approach is about disciplined thinking, not technical showmanship. You identify the key clue, choose a minimal test that aligns with it, justify the choice based on safety and scope, and summarize what the result means for controls and remediation. Replay Scenario 2 with clearer justification as practice. When changing an object identifier reveals another user's data, you classify it as IDOR, confirm with a minimal role comparison, document the unauthorized access, and recommend server-side ownership checks. You do not enumerate all objects or extract large data sets because one confirmed failure proves the point. When you can reason that way consistently, you are applying web attack logic the way the exam and real-world assessments expect. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.